take the scientific question based on what relates directly into our science. So there's a question from Sue Mohanty at iu.edu. His question is isotopic substitution going to change peak position or just the intensity? Wait, so you're asking about isotope leveling in Raman spectroscopy. It is positively going to change the peak position and not the intensity. Intensity can change in complex molecules. Most normal modes are mixed vibrations. So in many cases, like we have seen on isotopic substitution, the coupling with other modes change. And so you see a redistribution of intensity, but that's specialized. But the intensity apart, the position will change the most. And then there are caveats. For example, you are doing O18 isotope leveling and you're working with unleveled buffer, which has O16H2O. Any species that can exchange with your buffer will exchange. So that's a limitation. And in that case, you will see lower intensity O18 peak. For example, a metal oxo that rapidly exchanges with water. So if your metal oxo peak was this big with O16, with O18, it would be like this small, and there would be still left O16 peak. Okay, so that's my answer to this. Now, Shonchita says the popularity of this topic has witnessed a special issue. Thank you, Shonchita. I know her very well. She's alumnus of ICS. Okay, now J. Dave says if hydroxy radical is formed, it creates oxidative stress. Jay, this is a different topic, but I'll just comment on it briefly. Our body has mechanism, I'm sure you know of, like catalysis and different types of superoxide dismutases, which deals with the hydroxyl radicals. And you know hydroxyl radicals are generated from oxygen that you breathe primarily. So if you want to live forever, don't breathe. Just kidding, okay, breathe. Our body has antioxidant mechanism. You try to help it with antioxidant radical scavengers like vitamin C, thiols, you know all that, okay? Now, Sumohati, you already had a question. I have to go with the other ones. Please do send me this question in email or Facebook, wherever you want. I'll come to you. Yes, feral species formation is strongly influenced by second sphere interactions, which is why with this differently substituted porphyrins, we can accelerate O bond cleavage. Okay. Shubhojyoti has a question about cross-disciplinary research. He said that things have become cross-disciplinary as well as interdisciplinary. In lieu of this, one research fellow having materials chemistry background in heterogeneous catalysis, how he or she could select an appropriate proteoliposome and active biomolecule scaffold that's absorbed light. Look, look, this is a serious business, okay? Research is serious business. I know everyone is looking for sort of fancy, flashy cover page science. I'm sorry, I don't believe in that. I'm pretty old school when it comes to research. I believe in gradual development in one particular direction. I follow and advise that one of my IIT Kanpur teachers, P. Gupta Bhaya, gave me when I was a master's student. And he said, as a chemist, there are only three kinds. Either you like to make stuff, or you want to predict stuff, or you want to explain stuff. Okay, this is Pinaki Gupta Bhaya. If you want to make stuff, you're a synthetic chemist, you can make stuff. Enhance your skill on synthesis, approach the problem by trying to bring in your synthesis skills. If you like to predict stuff, you're a theoretician. Go learn theory techniques so you can predict. If you want to explain stuff or explain stuff, you're a chemical physicist, or you want to look at it, learn spectroscopy, seriously. That's a good way of explaining things. If Jyotishman is there, he's laughing big time. Now, Shetri says, recently it has been found that spin selectivity can control ORR mechanism. Effectively, if we control the spin of the electron during reduction, we can bypass peroxide formation. If we account for this effect, maybe we see a change in terms of conclusions. Shetri, I don't think I understand your question, but I think what you're saying is you bypass the peroxide by going from, how do you cleave the O bond? I want to know, because your superoxide has 1.5 O bond. Peroxide has one O bond. So if there is something specific in your mind, which right now I'm not understanding, because you have to climb down oxygen, superoxide, peroxide. You may reduce the lifetime of the peroxide. You may activate it with some approach, maybe start with a singlet oxygen. That's a different issue altogether. Okay. Now, do email me, Shetri. This, I think you're onto something interesting, but do email me because I want to know more about what you're saying. Rahul Kotani from Florida. Amazing talk. Thanks, Rahul. I hardly understand. I hardly think most people get it because I tend to speak more, but I hope you got the gist of it. Okay, can you tell me what the proton and electron source is in your catalytic system? Electron, because I'm doing heterogeneous electrocatalysis. Electrons are from electrode. So that's a solar panel or wall, grid, whatever you choose. Protons, water. Okay, buffered water or just water. Okay. Bhumika is asking which amine is good for cleaving O bond, primary, secondary, how? Well, Bhumika, this sort of is a complex question, and I cannot tell you that I know the answer to this completely yet. But what we found is you need to match the pKa of the amine such that the pKa is above that of peroxide. Now remember, we did estimate the pKa's of the proximal and the distal oxygen of the peroxide species, right? That was back in 2013, 2014. Based on that, we decided to put up amines having pKa above 6 to 7 because that's where we thought the proximal could be protonated, okay? If you make the pKa lower, the distal will have a higher chance of being protonated. If you think of Dan Nocera's system, his carboxylate. At pH 7 or 5, it is deprotonated. That is why it could not donate proton properly. But our systems have pKa which are higher than that of the operative pH, so it could actually give the proton to the intermediates. So I would say right now, from what we understand, amines having pKa above 6 to 7 in water. Okay, that's Abhishek Dey. Hey, another day. We are rare species in science, particularly chemistry. How can I design a catalyst for a particular reaction? All right. Because we're doing a Facebook Live, my students are going to laugh. They know what I'm saying. We have an approach called electronic retrosynthesis, where you design the catalyst by looking at the molecule you are targeting using ligand field theory. If you're interested, and because we are live, drop me enough line after Diksha's post in Facebook, then maybe I can be alive in Facebook again and we can discuss this, because I like discussing with students. So if you're into it, I can help you in what I understand, but remember, that's my point of view, okay? All right. Shubhajyoti Samanta. Hey, Shubhajyoti, you're doing too much, boss. You already did two. Now, he's asking if you can use these techniques of glycerol carbon species and in CO2 reduction. Oh, we are doing it, boss. That's what we are doing. So right now, it's being very difficult for reasons that any IR spectroscopist will understand. Right now, we are developing the parallel IR tool, but that's difficult. Doing a flow cell on a heterogeneous electrode using IR, the only thing known that works is the ATR approach developed by Fraser Armstrong and Kylie Vincent in Oxford, but that's impractical. That's why you take a ATR crystal, coat it with your electrode material, deposit stuff. Look, we are not that rich as a country. We need to come up with a system which minimizes costs to get better scientific result. And there you can do it, but that's still not steady state. So this is a different question. If you're interested in what we're doing, do drop by in our lab, my students, after the lockdown is over, of course, and don't bring COVID, or don't take it from us. They will help you with this. Okay, does same process occur in hemocyanin? This is Yogendra Kumar Lairi. Yogendra, this is slightly different, but yes, in the hemocyanin, you have similar peroxide species and their O-bond cleavage is rate determining, except in oxygen carrying, you don't want to cleave the O-bond. You want the O-bond to be intact, but a parallel enzyme tyrosinase that has a proton channel to cleave the O-bond. So I would not be blind enough to say it is exactly the same. I'll say could be similar, but remember hemocyanin does not cleave the O-bond. You do not want oxygen Okay. Using SIRS, if we have sensing, SU Mohanty, you are very prolific, boss. This is not my area. You want to talk about SIRS in sensing, talk to Professor Umapati. He has been doing this for 20 years. He can tell you more. The answer is yes, but I'm not an expert in sensing. Okay, as I told you, I'm pretty old school in science. I believe in growing in one vertical and learning along the process rather than and trying out different things because I'm not that smart. Okay. Ah, Jyotishman, where were you? Can you elaborate more on the pKa values of the O2 bound proximal and distal case again? Yeah, JD, I mean, see, okay, Diksha, I'm going to go back on the slides a little bit. Jyotishman is my subject expert, so I will respect his concern. Just other guys, you know, me and Jyoti, we are the JD, we are same batch. He was in IIT Kharagpur, I was in Presidency and IIT Kanpur. Then he went to Princeton and Berkeley while I was always in Stanford. And then he ditched me and he's laughing. I'm not going to tell you how, but he ditched me, okay? But that doesn't mean I'm not going to answer his question. JD, look at this slide up here, boss. See what you can see. Are you seeing the slide or the question answer panel? Ajay, please help me here.
Yes, yes.
All right. So, JD, the whole point is you see this guy over here, the hydroperoxide. It's basically the pKa of this proximal oxygen that leads to H2 to release. And pKa of the distal oxygen leads to O-bond cleavage. Enzymes like HRP has designed their proton channel with arginine, you know this, arginine and histidine to get the proton here. And it's not just orientation, it's also the pKa. See, the proton in arginine or in HRP comes from the histidine, which has a pKa of around 7. Okay, not with arginine, which has a pKa around 13 or 14. And that's respecting the pKa of this guy. Okay, once you have a protonated species over there, the proton has to come here. Now, the pKa of 4.5 that I tell you is for a free iron porphyry. But the moment you bring in a hydrogen bonding, for example, see this optimized structure over here. This guy no longer has the same pKa of this guy. Because what you have done is you have changed the product of protonation completely, right? So this has a much lower pKa, which can be achieved by this species, okay? The pKa is also tunable. That's why when asking that question, what kind of amine is better, I was conservative. But know one thing for sure, free superoxide, this is Joan Valentine, pKa 4.5. You bind it to a metal, it will be definitely less than 1. So if you want to protonate a superoxide, which is what Jimmy Mayer does, all his chemistry is in the presence of strong acid. Because other than that, you cannot protonate this. But if you are doing this one, hydroperoxide, that's what we do, you can play at higher pH and use weaker acid or neutral acid to get this protonation to work. I hope I answered some of your question. But you have my phone number, right? So, all right. How can we take this idea from real world? You ask a business entrepreneur and a company owner. You don't ask a basic scientist about real world. I know this is debatable and my position is very strong. Knowledge is something that only scientists can generate. Without knowledge, there is no innovation, there is no business. As long as you're acquiring knowledge, truly new knowledge, you are a basic scientist, keep on doing that. There was a post I did long time back on herbivores and carnivores in Facebook. Read it up. That's my position. As a trained scientist, you can generate new knowledge. Of course, you can do innovation. Innovation requires collection of all different knowledge. What we learned here, what JD's been doing with this charge transfer excited states, what other people are doing, bring it together and look for a solution. That requires engineers. That's where we are lacking. And of course, engineers won't do it if there's no company to buy it, right? So that's what we are lacking prior to that. Difficult topic, we'll come back to that, Mohanty. Okay. Now, band diagram of your system. This is not a condensed system. We don't have a band diagram. These are distinct molecules. Of course, my electrode is like a formulaire, okay? I apply an external potential. That's its potential. Now, this is basic reduction potential of the species on the electrode. So we don't have band diagrams over here relevant to the catalysis. But in material system that we do, yes, of course, that's important. Does the number on mechanistic study depend on enzyme to substrate ratio? Well, yeah, I mean, of course, these are second order kinetics, substrate and enzyme reacting. If you have side reactions and you don't have substrate, so of course the side reactions will give you more product. So in a way, yes. Vikas Dikshit, the oxidation of adamantine tertiary get oxidized, but on the basis of cavity size. No, yes, Vikas. Look, this is a balance between what's easy thermodynamically and what's easy kinetically. Kinetically, the secondary is easy. So you could look at it both ways. Tertiary, easy to oxidize, getting oxidized, right? Secondary, not easy to oxidize, not getting oxidized. But when tertiary is not getting access, secondary is, you will see secondary oxidation in preference to tertiary. That's what you see. It's a balance between thermodynamics of CH abstraction and kinetics. Kinetics preferring less hindered species. And remember, secondary alcohol CH that you need to oxidize to go to ketone is a tertiary CH, which is why we get cyclohexanol and not ketone. Saurav Beige. So my question, don't ask me, sir, I'm not alone, is that why you use only iron rather than kind of inexpensive? This is not an enzyme, sort of. My whole idea is learn from enzyme, do it with synthetic systems, okay? So if I go back, these are the crystal structures of system I'm using, for example. They are not enzymatic system, they are synthetic system that you can do in the lab. But please realize, I'm not trying to solve what's problem. We are just trying to generate information that one day might, okay? Does the cycle go on? Yes, it does goes on. That's where turnover numbers are being generated from. A turnover number of 20,000 is 20,000 times the cycle has gone on. How about the oxidation of methane? Nagaraja, I would have loved to tell you that we can oxidize methane, but methane generation and storage in cylinder is risky, and I don't let my students work with methane that easily. We could generate methane from carbide and everything, but the idea is I can go up to 100, 105. We have done octane and cyclohexane, normal hexane, and we're getting reactivity. So we know we can do primary CH bonds, but we have not done hexane because of safety. Of course, you can try, take this system, do it in your lab. If you have the setup, I'll be more than happy. Vishal, SIRS. Okay, can SIRS influence the mechanism? Very good question, Vishal. The mechanism, the chemical steps are of the level of millisecond order, okay? You look at the rates, right? 1,000 second inverse, something like that. That's your diffusion control rate. So the lifetime of your chemical reactions are of the order of milliseconds. But your SIRS phenomena and the vibrational features that you're doing, they're done by picoseconds. So of course, when you're probing your excited state, the optical and the vibrational excited state, what you see is an average through the reaction time. So I don't think that's a problem. Okay, what do you think whether discuss molecular catalyst can be practically, I don't know, about devices? I must say we have used our hydrogen catalyst in fuel cell, which is not discussed here, in fuel cell devices, and some of these in ORR devices, and they're working, but as I told you, I'm not an engineer. To the best of my capacity, I'm a scientist. I can generate new ideas, I can generate new knowledge, but if you ask me if I can generate technology, I'm not that arrogant, I'm not an engineer, and I know the importance of engineering when it comes to making actual device. That much I've learned to respect. Shukanto, what makes distal? It's the distal oxygen having higher proton affinity than proximal. Shukanto, it's the bonding with the iron 3. The iron 3 has a sigma bond and a pi bond with the oxygen, but overall the electron density on the proximal oxygen is still higher than what would happen when you protonate that, which is why the distal is lower pKa or lower proton affinity. Okay, it's the bonding with iron is not as good in delocalizing the charge as a proton, because proton really gets rid of the charge. Ranjan Patra, I know this name. Hi Ranjan. For oxygen reduction, energy is released and how, and is not hot tissue in fuel cell. Ranjan, this is a great question. Yes. If you ask me what is the biggest energy problem, it's not hydrogen water splitting. It's not knowing how to deal with overpotential. and how to use the potential to actually do something else. Look at CCO. CCO at pH 7, the average potential for oxygen reduction is 0.8 volt, 0.83, pH 7, right? CCO works at 0.4. Where does this go, this difference? This goes through proton channel all the way to ATP synthase to become mechanical energy, the proton gradient, and store the excess energy as chemical energy. No synthetic system has so far even tried to do that. I don't know many people who are trying. I tell you this much, we are trying, and I'm not going to tell you more than that because I might not succeed, right? I'm ashamed of failure. No, I'm not. We are trying, and hopefully one day we'll see how we are using this extra energy to drive other catalytic reactions or non-catalytic stoichiometric reactions, maybe, okay? Is your iron system, this is Rahul Hutani, is your iron system selective toward dioxin activation, or can other, yeah, I mean, it can, you know, iron is basically a paramagnetic system with a lot of electron density depending on what oxygen state. We have used iron to do peroxide, we have done iron to do CO2, proton even, so it can do, but nature has used iron to do oxygen and proton. So that's my answer to you. What's the potential? Potential is around against NHE pH 7 plus 100 millivolt. Can we use porphyrin as singlet oxygen generator? Shomik, I think you know the answer to this. A lot of people have used gadolinium porphyrins and corals. I don't know this field, so I'm not going to comment on it. I believe if you look at work by TKC and even Hydroperoxide in our institute, and of course Ravikant in IIT Bombay, they have done splendid work, so they can tell you more, but I'm not an expert. I believe you can, but anonymous attendee, I wonder who this can be. What is the difference between HAT and PCAT? Big difference depending on who you believe, right? I'm with Sharon, another person, Sharon Hamschiffer. I believe that they are different in where you get the proton and electron from. Jimmy Mayer disagrees with us. He thinks they're all the same subclass of same reaction. But look, this is a complex topic. If you have asked the question, you know how complex of it. Maybe we can discuss it separately. This does not relate to the big audience that we have right now. Arnav Datta, hi Arnav. Congratulations on your ChemCom Emerging Award. Do the presence of the secondary element change the pKa? Yes, Arnav, I was addressing Jyotishman. I don't know if you heard it. Yes, it does. And I cannot tell you how much, but we did compute, Autonu did compute the delta pKa or delta PA translated to delta pKa. And we have an idea, it's a couple of units, not negligible. So yes, it does. Because you're stabilizing the product side of that reaction. How electrode was modified? Generally, you could do it two ways. If you want fast electron transfer, you take a graphite electrode, H-plane. It gives a lot of surface for the porphyrin with the aromatic ring to stick. You just add an organic solution like dichloromethane, drop cast it, rinse it off with dichloromethane, sonic in methanol, get rid of all the excess porphyrin, have a nice thin layer which you can judge from the CV response, and then you dip it in water, do your chemistry. For SIRS or slow electron transfer, you do the same now with gold, high modified gold and silver electrode. But for coordination that we use, you use a mixed monolayer where you have mostly hyols, but around 10% you have imidazole, phenols, hyols interdispersed, which can be used to bind the porphyrin. And you know how much porphyrin you're putting by integrating the CV. How could you explain the formally spin-fit and forbidden reactions, triplet or with singlet? You know, this is something that's tricky. Here, you see, I mean, you know, I know spin forbiddenness comes into play, but think about this. Copper 1, D10, does react with oxygen, and it gives you copper to superoxide, right? So the spin forbidden issue that you would always hear is because transition metals are paramagnetic, they can stabilize or they can allow spin forbidden reaction, which is not really the case. Because copper 1 is a transition metal, it's not paramagnetic, it can react with oxygen, nitric oxide, paramagnetic species, resulting in paramagnetic space, this thing. So there's a backstory, maybe someday later I'll tell you, between me and Dan Stack on this. But the issue is, can you stabilize the transition state? So you have a dimagnetic species, you have oxide triplet coming in, when you look at the reaction profile, and Anand Datta in our institute does a lot of this, there are going to be transition states of these spin crossovers. Can you stabilize them? Now, the easy way to stabilize is by using huge exchange interaction of the transition metal complexes. And that's why transition metals can do them easily. But when you look at first row metals like carbon, nitrogen, they don't have very good spin orbit coupling constant. They're not good at that spin crossover. So there's a problem, right? That's why you need to light a fire or give it catalyst. Okay. Sanchita asked, what is the fundamental strategies to extract the grassroots synthons if small stable from its comfort zone? Yeah, I mean, Sanchita, that's what I was telling. If you're interested, we can discuss at least how I approach things, and I've asked my students to think about electronic retrosynthesis, and that would be nice. It's too involved, but as I tell you, it is not something you already don't know. It's a combination of ligand field theory and molecular orbital theory. Okay. Shubhankar Pal, PT, ET, PCET. Shubhankar, this is easy. PT, ET, and PCET is PT, ET. I mean to say easy as a definition. You do a proton transfer distinctly from an electron transfer. PCET, where you do them together, and you have this Purbe diagram. Shukanto Mondal in IIT Kharagpur, and then Amit in IISER Bhopal, Swayam Chendgupta, they're really good with PCET. And if you have access to them, talk to them. So they will tell you that you do an electron transfer, proton transfer distinctly, that's PTET, or vice versa. PCET, where they're coupled. So the electron comes in while the proton is coming in, and it's difficult to deal with quantum mechanically, which is why you have Sharon Hamschiffer really trying hard, coming up with a new way of addressing this. And one of my junior colleagues here in ICS, Abhishek Das, he's also trying to do that. Biman Jana. Biman, you could have just asked me the question. He's my ICS colleague. Biman, I do provide, he's asking, in case of increased electron transfer, if I increase the electron transfer rate but do not provide very slow proton transfer, what do you expect will happen? Well, Biman, what will happen in those cases is I will see more of H2O2 coming up. More of H2O2 will come up because the proton really needs to go to the oxygen with a lower pKa. So if I don't do this with more electron transfer, we're going to generate more electron transfer and no proton transfer. We're going to generate hydroperoxide. But wait, the issue is, if you, along with electron transfer rate, if you give it more thermodynamic push, so the iron 3 hydroperoxide becomes iron 2 hydroperoxide, then what happens is the basicity of this oxygen increase because you've added more electron. Then the proximal oxygen, which is further away, distal oxygen, has a higher kinetic access to protons, and boom, you'll cleave over bomb. So it's not just a matter of kinetics, it's also the thermodynamics of the process. K. Sundarwal, hey, I know where you're from, Sundarwal. Is it possible to perform different dioxygenous function using single molecule by tuning the redox potential? Well, we just arrived at this point, and I don't know, Sundar. I mean, it sounds good and something fantastic that I should try, but I'm telling you, my student who just did the work is really now blaming you for putting this idea in my head, right, Manjishta? She's smiling. Okay, but yes, in principle, if we control the speciation, we should be able to, and we're trying, okay, we're trying. Can you employ a Lewis acid at the super, well, you know the non-im area very well, right? So Tufan, are you who I think you are? Okay, you know, I know Tufan. Tufan, you know the non-im iron area, Vangunam, Kallo, Larry, everyone else, Tapan over here, they have done this with this, activating that. You see what I told you about Jim Mayer, right? How he's doing his oxygen reduction is iron 3 superoxide with this strong acid. You put a scandium, that's a strong acid, right? You've seen the work by Wesley Brown. Scandium is essentially a source of triflic acid if you have a little bit of water. So that's how this activation has been working, Lewis acid or protic acid. So yes, you can, but I don't want to do that. I want to be in the neutral region. That's what I want to do, and my students want to do. Yeah, and that's what Devendra Kumar is saying. Can scandium triplet? Yes, Devendra, same issue. You see, I'm at pH 7. You add scandium triplet, it's all can scandium oxide and triflic acid, and my buffered solution. So triplet anion. So yes, in organic medium, that's how people do. You can do it. One Munam and explode heme in that, not dioxide, superoxide species with scandium triplet, but you can do it. Okay. Maybe wait for future when photocatalysis as well. Sumanta, it's up to people to, listen to me or not. This is not flashy science. I don't have cover pages. So, as you mentioned, the turnover number reactions high. Does it mean the yield of the product? Yeah, I mean, when you, yeah, you're definitely a non-immediate person, anonymous attendee. The yield of the product, when you do from, it's easier to do when you do a single turnover condition. We are doing under catalytic conditions. When, for example, when we are oxidizing cyclohexane or toluene, for example, with molecular oxygen, the GC trace shows at the end of the reaction, we hardly have any toluene left. And Munjishta, if she's in the audience, she can probably chat in and tell me, we have no toluene left. We have cyclohexane gone maybe 30%, okay? But we are competing with the self-decomposition of the catalyst. But in cases where the CH bonds are weak, we see almost very high conversion. But with tough CH bonds, the conversion rate is low. I cannot tell you exactly how much it is. It is, the turnover numbers are quantified with respect to catalyst that we have and not on the substrate. But we do see the substrate GC peaks comes down over here and the product is over here in most cases. Okay, but I have not quantified that. Mile, hi Mile. What's the role of steric on the proton electron transfer? Are they same for both? Well, Mile, the electrons are coming from here and the protons are coming from here. So the sterics is up here. And it's not the sterics, Mile, it's also the proton channels we are creating with the amines, protonated amines. They're actually helping, right? If anything, picket fence type steric will disallow proton access because it's hydrophobic. So you need this proton translocating residues that we are doing and Dan has done with the carboxylates in the past, right? The electron is coming from here. So there is no steric hindrance. That being said, you should look up a paper that Shobhoshachi and Bandopadhyay and we did in IC where we calculated the reorganization energies for electron transfer for iron porphyrins, 6-coordinate, 5-coordinate, hydrogen bonded on this electrode. I think you're going to sort of find the answer to what you're asking out there. Okay. Single molecule catalyst. Well, if it is SIRS active, Sundar, you might, but isn't that where you really dilute stuff up? So not single molecule protein, I know what it is, but single molecule catalyst, the idea is you create molecule type catalyst in different level. So if you can somehow get signal out of that, I think there is a bunch of really good group. One in, Tom Jaramillo. He is doing stuff, not in operando yet, because he does mostly of STEM and all that. But I believe there are a couple of Chinese groups who are trying to do in operando XAPs with single molecule catalysts. So there is work going on. Okay. Rahul, how do you distinguish between frontal? Rahul, this is nomenclature, not by me, the protein people, Poulos, and even before that. Proximal, if you have iron and you have oxygen bound to it, that's proximal proximity, really bad these days in COVID. And then there's distal, which is not bound to the iron, but part of the molecule, social distancing. Okay, ionic liquids, how use ionic liquids as catalyst? Manoj, I'm not an expert. Sorry, brother, I'm not an expert of ionic liquid. I cannot help you there. You might want to ask, there are a lot of NCL groups in ionic liquid who do very good work. Okay, so you can answer, sorry. How relevant is tunneling? Rinjim, most of the electron transfer that we do are tunneling over here. This is something established by Royce Murray, late 80s, early 90s. So we are using his method, which is later sort of modified by Chipsy. So they are tunneling in the region where we are doing the catalysis, except for short chain, where you see a lot of hopping, I would say, through space electron transfer. One of my students, Shomir Chattopadhyay, is really digging deep in this, and you can look up one paper where we saw isotope effect on thiol and deuterated thiol in this electron transfer. It's in archive because nobody is letting us publish. Okay, so, oh, Mohanty, welcome. Kyle, nice talk, Professor. As you are doing resonance round, what is the wavelength? The wavelength, I'm tuning into the Sorey band of this porphyrin, which is around 400 nanometer to 415, which is why we are using silver as our electrode during SIRS, because that's where the plasmon lines of silver are. Okay, you can use other wavelength. For example, we do Raman on gold substrates for different systems. We use 600, 647 nanometer to tune into the gold plasma. Okay, Chinte, is there a possibility to have a 2+2 electron transfer? You know, if H2O2 comes out during the reaction process, imagine you have a hydroperoxide and you have H2O2 coming off and rebinding. We are rotating the electrode, right? So we have solvent constantly washing the electrode. That is how we detect the H2O2 on a ring. So in this, I would say chances are less. But if you did not move the electrode, in principle, yeah, you can have it, provided you build up enough concentration of H2O2. Bhavatosh, hey, Bhavatosh. I understand iron is probably the best. Yeah, Bhavatosh, I sort of answered that. I used iron because nature used it and I have bioinorganic background. With other manganese and ruthenium, seriously, I mean, talk me into doing this electronic retrosynthesis stuff, okay? And you will sort of get an idea of how I would advise anyone to approach activation of a small molecule. Okay, Ashish, good afternoon, Ashish. Srijita Basumalli, is there any detectable OH radical? No, Srijita. OH radicals, in our cases, if they are there, we would detect them the same way we are detecting H2O in platinum ring. So whatever is there is taken into account that 1 or 2% partially reduced oxygen species we see. So not a lot, okay? How did you calculate iron oxygen backbonding percentage? Oh, I used molecular orbital theory analysis of Gaussian calculations. So these are molecular orbital diagrams coming out of Gaussian calculations. We do MO analysis, and that's how we get that. How tolerant to acidic system? Good question. Not so much, not so much. Iron porphyrins by themselves, you can go to acidic system, they will work fine. They change from oxygen reduction to water to mostly H2O2. That's what Fred Anson and they did a long time back. For the molecules we made, some of my students, we were looking at the pH dependence. The ones with high pKs generally get protonated and then they degrade really fast. We don't know exactly how that happens. So these ones, the ones that you see on the screen, are probably not very stable. I said probably because it's tentative, okay? Reusability of the catalyst. Well, the catalyst will decay, but think about it. We have this, not in this case, we have an electrode carrying thiols and imidazoles and phenolate, and your catalyst dies. And we demonstrated this in inorganic chemistry paper 2013, Kushal. You just wash the system with acid. All the loosely bound iron comes off, and you can load it back with the same catalyst, and you go to get recyclability. So that much you can do, but the catalyst will die, okay? Yeah, Bhavatosh, don't worry, your typo, we are all typing, I do it too, but it's difficult. What element you're going to choose is probably as important as the question, what's your substrate, and more importantly, what's the ligand field and d orbital occupation of the metal, but it's all substrate dependent. Can you explain the estimation of pKa of the superoxide? Well, free superoxide has a pKa of 4.5 in water. This is John Valentine, Jacks, PNS, 1988-87. Whatever species you bind to a metal, because the metal extracts electron density out of it, it's an anion, the pKa becomes lower. So that's my estimate in saying the pKa of the superoxide species is metal bound species is definitely less than that of free superoxide, which is 4.5. That's my estimation of pKa. And what I'm citing as an example is Jimmy Mayer and even Shannon, who are protonating the superoxide. They're using strong acids, that is very low pKa, to deal with this. Shambhu Chatterjee, is there column chromatography required synthesis? You have no idea. Somewhere my students are laughing because this slide, they always say that I skip by 2 minutes during a presentation, when this is what takes 80% of the time. Now they should be happy because I have had in the background for at least 15-20 minutes. Right, Shamishta, you're happy. Amman, Shubro, you're happy, right? Okay. We do a lot of column chromatography. Can we not develop in situ some super fast peroxo or in the body. Okay, superoxide dismutation in our body has a second order rate constant of 10 to the power 9 mole inverse second inverse. Nature has done what you are asking us to do. The problem is we are generating too much superoxide. The problem is we are not natural, right? We are doing too much random stuff. We are not eating healthy. I smoke cigarette. It's my fault. Nature has done everything. The human body is engineered to last long. It's us, right? You do exercise, you generate superoxide. You starve your body of electrons, vitamin C, thiols, you start generate superoxide. You do this, you generate superoxide, right? So whose fault is it? You live on, remember all these mythological sadhus, what did they do? Their life, just this, nothing. Live 1,000 years. All right, Mayuk, hey Mayuk, how are you doing? Have you looked at system with protonated scaffold bonding them through instead of protonated scaffolds? Well, Mayuk, the second sphere hydrogen bonded, the one that you see in the screen, are protonated at pH 7. That's sort of the framework we're using here. The pKa of this primary amine and guanidine, the synthesis is not shown, but that paper has come out. At pH 7, they are all protonated. And that's kind of crucial for this initially hypothesized activation that I was talking about, this particular protonated amine. This was necessary to activate the peroxide, and we established that, at least experimentally. Of course, we can't get crystals like you do, but we get reactivity. We established that using this stock flow data where we see very low peroxidation. Okay. Now, Sunny from Kalyani, can pH 5.6 of heme catalysis be electron transfer? Can make iron for? Oh yes. That's what we did, son. We did slow down electron transfer, right? I mean, look, that's what we did. I mean, look at this whole idea. What we did is we slowed down this electron transfer, which was causing it to reduce oxygen to water. Instead, we use this high valence species to oxidize substrate. So yes, we can. That's the whole idea. Bhaskar, IT Monday. Hey Bhaskar, how are you? I was wondering whether proton shuttle mechanism through water was considered along with the amine for the O. Yes, Bhaskar, I mean, so something that I'm doing with my younger students now, Sudipta Mukherjee and Abhijit Nayak, is we have systems where you have multiple protonable residues. This sort of relates to what Mohik was saying, and crystallographically we can see water channel, okay? And we have pretty exciting result where we can actually switch between push and pull effects, right? We are writing it up. The science is not perfect yet, but hopefully soon. And yes, we are doing that. And Shormishta, she is doing the same with increasing number of amine residues. And yes, oh yeah, of course. So there is a paper by Andy Gewerth. Andy shows that you can, and also by, Arnav Dutta is in the audience, he's laughing. And Jones from PNNL in hydrogen evolution, where they actually use proton shuttle to increase proton diffusion near the catalyst. And that accelerated the rate. So Andy did that with copper catalyst in oxygen reduction. We have done it for iron porphyrins. We just never had the time to write down because I'm really slow in writing paper. Even though it gets rejected, we take like 2 years. Imagine if I wrote early, we'll get rejected every day. So I'm not very good at writing papers, okay? So yeah, Bhaskar, we have. Yes, Rahul, you can generate iron nanoparticle on the electrode. A lot of people have a specialist on it. I'm sure a bunch of JNCS people, they can help you with that. They're in this. They have really terrific material science people, a lot of good friends, and they know everything about iron nanoparticle and SSU, ISC. They know everything, right? Even NCL Pune has great catalysis, heterogeneous catalysis. Can you elaborate more on the structure of the 3 classes of catalysts? Yotishwani, you need to elaborate this one more. What do you mean the 3 classes of catalysts? I'll wait till I scroll down to your question and then I answer sort of more explanation of the question and then I'll come back. Rajshekar Roy, where do these complex stand regarding water rate and selectivity in comparison? Look, Raj, the issue is you understand these are molecular catalysts and I'm looking at single monolayer. Okay, the moment you go into material catalysts which are porous, your electrode is no longer monolayer. Electrode is this thick. So it's unfair to compare a monolayer on 1 square centimeter with a monolayer 1 square centimeter, which is in reality 100 nanometer thick catalyst bed, right? The same article, microreasons for nanozymes. Nanozymes are big nanoparticle, thousands of nanoparticle centers. You cannot compare them with enzyme, which is 1 center. You have like thousands of centers. So you have to factor that in. So how you quantify that brings into the question. These are selective, but the material is always going to be more stable. All practical catalysts which are heterogeneous are material catalysts. That's what you have to do. What we can do is sort of give you a hint as to how you may be able to improve it. That's all we can do. Okay. A question that we always face: as I develop catalyst for coupling reaction, they always ask reason for developing catalysis, metal cluster removal, whether these reactions are possible with simple metal salts. Well, it depends on the reaction, right? Let's say you want to degrade lipid into just blah, all kinds of product. You add H2O2, iron nanoparticle, it will do a bunch of penton, it will degrade lipid, no issues. But you want to do a selective transformation. Of course, you need to design catalyst. Why on earth do you think nature would have 57 plus and counting genes of cytochrome P450 alone in our body, right? If anyone tells you that, look, what would happen, why can't you do it with simple, then you say, you know what? Replace your metal enzymes with iron nanoparticles. See you in 20 milliseconds. But also you have to be really genuine in your approach, because there is fallacy there, right? There is a lot of horizontal exploration, doing the same thing over and over with slight variation. You need to be more upfront with the funding agency or paper why you're doing it. As I told you at the beginning, if you ask me, I find doing research very difficult, because it's not just having an idea. It's an idea for what? It's an idea for more of the same, or idea for gaining an insight, learning something that nobody in this planet knows. And what I always tell my student, be the person who understands something of general importance, which matters to hundreds of chemists for the first time in the history of the planet. And then rejoice the moment for a year. Do nothing. Keep on perfecting that. Keep on testing that. And then only you write your paper. Don't jump into it. Okay, science has a 300-year-old history. Not easy doing science. Publishing paper, Diksha is here, she knows. Okay. Sir, proximal Ritik plays great role in forming. Can we study O-bond breaking, changing the proximal ligand? Well, yeah, I mean, people have done that, right? Von Unam and all that, they have changed, and there's this competition between, you look at Fuji's literature, Hiroshi Fuji, Osaka, there's competition between homolysis, O-bond, heterolysis. Yes, of course, you mean the actual ligand. It can be done, but the problem is, you have thiolate, iron porphyrin, and you add peroxide. The peroxide will go for the thiolate first, right? And if you want to know why, read the PNAS, me and Nikolai we did in 2016 with P.K. Das. It goes for the thiolate. It doesn't go for the iron. So that's the problem of studying this in solution. But look, here you have an electrode, thiol from here, catalyst. H2O is not being able to access it so easily because it's full of hydrophobic. And that's the advantage why we can do what we can do, I think. Okay. Apart from protonation, can you? Yeah, I mean, that's your push effect, thiolate. You increase electron density with the iron 3 hydroperoxide, increase the pKa, so proton will come. That's Mike Green, right? Mike Green showed us that. Before that, John Dawson, he showed us that, right? Now, the problem is you have to make sure, though, the oxygen goes to not the proximal, the distal. If you do proximal, you get H2O2. This is called uncoupling reaction in P450. P450 arranges the O-bond cleavage using push, but also the protonation onto the distal, which it does by the threonine 252 residue. That's an alcohol, hydrogen bonded to an aspartate. It gets the proton where it needs to go. You mutate the threonine, you get H2O2, uncoupling. So you don't need residues that can protonate, but you definitely need residues that will do proton transfer to that distal oxygen. So if we design such a homogeneous or heterogeneous catalysis that already contain oxygen species, then can we do the oxidation? Yeah, I mean, that's what Larry K, Carl Wigger, they started, and now Shyam Chandgupta, Shastri, Tapan Pine, they're all doing, right? They transfer, they make this iron oxide species and start their catalysis in solution. Yeah, in him, Monmunam, J. Groves, they have done it for a while. In solution, you can do that. Shagnik, really? Shagnik, you're awake? Or this is a different Shagnik. For SARS RD, do you take Raman data at various potentials in order to probe? Yes, Shagnik. We do take data at different potentials, and we have gotten better at it. Kushal and Shudit initially, they were miserable because the signal to noise wasn't very good. So we had to collect our data before the catalyst degraded, and we had to make sure it's reproducible. And they worked really hard to get that. We used to come in really early to avoid vibrations because we were in the second floor. If you're Shagnik Chakraborty, I'm thinking of, now we have gotten better with the microscope and better optics. So now we can collect data within a second. So within a second or a minute, 10 seconds, 30 seconds, we get good data. Monjishta is taking advantage of that, or Bhattov is taking advantage of that. And now we can actually go into these high resolution questions. Too bad for them, that's life. Anirban Bhandari, is it possible to crystallize? Yeah, I mean, Anirban, heme iron oxo, to the best of my knowledge, has not been crystallized till date out of a protein because they are super reactive, although one Munam is not going to buy that, but they are, which is why they cannot be crystallized. But there are at least, Shyam, please type the response if you're there, more than 20, 30 crystal structures of non-heme iron oxos. Yes, there are. Gaurav, no questions. Just want to say, even though you talk slightly fast, you still understand because engaging presentation that keep up. Thank you, Gaurav. I know I speak fast, sorry. People say it's the Bengali in me. And when I went to the US, a lot of Indians say it's the Punjabi in me. I really don't know. Maybe it's the Benjabi, Bengali. So can you please explain the theoretical aspects of this topic here? This is difficult. This is a very open-ended question. Please do write to me and maybe we can discuss over Zoom separately because this is going to take forever because I don't know if you understand. Whatever I'm telling you about P450, hydrogenase, all that, that's a summation of my entire life learning of bioinorganic chemistry and how enzyme works. And I try to teach that in ICS in my own course. So we can have a detailed discussion where you can ask me questions and that would be nice. And I would welcome that because as you know, Gaurav said, I'm a Pungali. Now, Nipa Chongdar, when you designed the catalyst, did you take inspiration from the proteins? Yes, Nipa. That's where we start from. It's sort of learning from what we have and then combining the knowledge from the protein to evolve into better. Remember the original slide about diagnostics approach to catalysis? I strongly believe in that. Professor P. Kumbhakar, hey, Professor, thank you for your compliment. Vishal, thanks Vishal. Jointa, hey Jointa. Jointa and we know each other. He's doing very good work. He's in our EAB. If I'm not, or soon to be, we'll see. That prevents the oxidation of the ligand CH bonds. Jointo, it's if you look at the catalyst design, these are aromatic CH on porphyrins. That's kind of the reason why they are strong. And the other thing is, if you look at the structure of this, your metal oxo is sort of in the middle, and the CH bonds are extending up. So there's a steric hindrance, but they will die. They will die eventually. But if you have a substrate competing with your ligand, of course you will win, which is why these catalysts die, right? Otherwise, we would keep on going, and my turnovers numbers won't be 20,000, it will be 20 million, but they're not. So they do die. But the stable CH bond really helps in aromatic. Shantanu, hi Shantanu, how are you? Great talk. My question, what is the diffusion constant of hydroperoxide? Well, Shantanu, hydroperoxide species diffusion constant depends on the solvent. In water, you can look it up. It's going to be slow, slightly slower than water. Okay, kind of diffusion constant. Is there a, no, you're asking an electrochemistry question. Is there a relation between charge state of the, yeah, of course. Diffusion constant, you look at Stokes' law, right? Of diffusion. You have the size in there, right? So yes, there is this thing, and people doing dynamics will answer this question better because they think of this gyration, radius of gyration, or what they call it. Where maybe I'm speaking this wrong, Biman Jana can correct me. That's why the whole molecule as an ion with its solvation shell and counter ion moves together. So that's going to be slowly diffusing than a neutral molecule like water, which is hydrogen bonded, which is going to be even slower than maybe hydrogen gas, which is nothing and it's moving around randomly. But even that moves this sort of disturbing the hydrogen bonding network and its dynamics in water. So yeah, it's always dependent. Is there any commercializing your device? What device now? You want to commercialize ideas that are published, do it. Make good catalysts, save lives. Please. I cannot commercialize because I have no engineering expertise. I think I'm better off learning new science and maybe knowing how to make it better, right? Vishal, hey, welcome, Vishal. How can we determine the rate determining step during ORR? Well, that's where this technique really came from. What we decided is in electrochemical system, and that's why sort of I was complimented by Jean-Michel Savian. He said the reason why he's a very senior electrochemist. The reason he found our research interesting is because we were looking at the species on the electrode under operational conditions. See, the reason why we can say the iron 3 hydroperoxide is the rate determining step is because we see it accumulate in steady state. Anything that accumulates is, if you look at steady state kinetic premises, is the rate determining step. That's how we knew that was the problem, which is why we went back and we made corrections and tested them independently in organic solutions. And yes, we could enhance the rate of oxygen reduction by 2 orders of magnitude. So yeah, that's how we do it. How do spectroscopically we determine, I think, organic, inorganic, hybrid nanoparticles? Excuse me. That completely depends on the spectroscopy you're doing. All right. You're doing SARS, plasmon-based techniques, nanoparticles give you very good enhancement, right? And if you want to use optical tweezer, talk to Praveen. He's doing wonderful work over there, right? And now, other than that, if you're looking at bulk spectroscopic techniques and they are not enhanced by nanoparticle, you have a problem. Let's say you're doing NMR of an organic linker on nanoparticle. Of course, the nanoparticle paramagnetic effect is going to drown everything. So you have to sort of, that's how we developed our techniques, because we are trying to address that. So you need to have a very defined question and then think of something. You know, I do believe in something my PhD advisor always said, that with the right combination of techniques, spectroscopy, you can address any problem. So it's about coming up with a combination or developing what's lacking, sort of what we did here. Okay. Aniket, can substitution on amine influence? Yes, Aniket, it can. If you look at, there are slight difference if it's a primary amine or predyl amine. So there is, and we are seeing more of this in hydrogen evolution reaction with this iron porphyrins, where you have this amines giving proton to metal hydrides at the center. And we do see that the rates are higher for amines with lower pKa. And it makes sense, right? Because an amine with higher proton affinity, higher pKa, also has a stronger NH bond. So the transition state leading to the cleavage of the H bond is going to be higher, so slower. It will work, but it will be slow. So whenever Somishta can finish that paper and we can publish in 2 years, you can see more of that. Would you agree that it would be an ideal holy grail when the oxidation is carried out in absence of external protons? Well, you're talking about dioxidase chemistry, aren't you? Because if you want to do monoxidase chemistry, you need 2 electrons, right, from dioxygen. What you're talking about, yeah, I'm getting an idea. I'm willing to bet on who this anonymous is. Yes, Shoyom, you can take oxygen, take 2 iron porphyrins, split it up, and make CH bond. That would be wonderful. But you see, you're using dioxygenous principle and you are limited. It is Shoyom if it is you, if it is not, if it's Kolol, it's you or Topon, you guys are doing this. Now, yes, but you are limited to 2 electron oxidation of iron 2 to iron 4. That's not as strong, unless you're high speed, if you believe what's going on, as something like compound 1. But if you're using Tamil, that's why I keep on saying Shoyam, you can generate, if you can, iron 5. Maybe it's active, but we don't know that, right? Because your Tamil is a very electron-rich center. It will neutralize the electrophilicity, okay? Shujoy Rana, dear, can you please highlight the mechanism involved with CH? Rebound, oh, yeah. All right, Shujoy, so here is the mechanism that we think. So what's going on here is sort of an H atom by the compound 1 species, and this has an isotope effect of around 10 for cyclohexane and deuterated, and then a rebound. Now, you would obviously wonder if we did 2-methyl cyclohexane to see if stereochemistry is being retained. But you see, our problem is you take 2-methyl cyclohexane with the assumption that the oxidant is going after the tertiary CH, the one where the methyl substitution is there. But in our case, that's not the case. We see 2-methyl cyclohexane, we use it, it goes after the secondary, which is sterically, and so it produces diisoisomer. So yes, we don't know it's rebound from doing that, but we'll see. But we cannot use the regular probes. Okay, if you can think of more probes, you can send it to us. Okay, how we can determine the rate? I think I answered that using Sarzardi and the population. And there's a repeated question. I don't know if it's not clear. If it's not clear, please do write to me and I can discuss more. Gayatri, the temperature of the electrode that you mentioned, I'm in UV, I'm not in IR. So that component is any blue less. Secondly, we are dipped in water and we are constantly rotating the electrode. So it's getting flushed out. We did worry about the temperature going up, but that generally shows up in differences in Raman spectrum, you know this, but we don't see any difference in Raman spectrum in solution and on the electrode. So we don't think that's an effect. Have you looked at H22 production catalytically? Yes, we have. Oshmita has something, she's now doing a postdoc in Stanford, where we can convert selectively oxygen to H2O2. Yes, we can do that, but not published yet. Mosbar. Aditesh is asking, you did it with Raman, why can't you do it with Mosbar? Aditesh, there are two issues here. Mosbar, if you know the technique, you know it takes much more time to get signal to noise because Mosbar is a recoil-based technique and signal to noise take a while. Secondly, you have to design a cell. Look, I'm not saying it is not doable. It is doable. Something that I always keep it written over there. The sense of impossibility is the beginning of all possibility. It is doable. It is always doable. It just requires very creative design. Okay, so you need to come up with a Mosbar cell where you can do in situ electrochemistry. Okay, forget dynamics for the in situ electrochemistry and collect the Mosbar and slowly improve it. Don't think of a setup that's going to give you a paper tomorrow. Then you will never try to develop anything that seems impossible. Think of a setup that everyone thinks is impossible and has given up. But you know, if you can do it, everyone will learn a lot. And then you start developing it. This I speak more to postdoctoral candidates and assistant professors. Okay. If you think of immediate benefit, the time in science is probably going to phase out before, you know, anything. Or the war between TikTok and YouTube, you know, it's like a 6-week war. Who cares? Aurodip, I have two questions. Is there a vacant site present in iron porphyrin? If there, then does the solvent employ has some mechanism on the rate of catalyst? Aurodip, the iron porphyrins, generally the open side, when you reduce them on the electrode, you reduce them, iron 2, this comes off. Or maybe a weakly bound water. And then oxygen goes in, water goes out. We know this from hemoglobin literature that this rate of displacement is rather fast. So I'm not worried about that being an issue. Arnav Nath. Seriously, Arnav Nath is my wife, who's my colleague, her student. We have co-authored paper and he chooses to ask a question in a webinar. Can PCET and HAT be distinguished from the rate constant values? Arnav, it's not that easy. It's more, you're in lockdown, that's why you're doing it, I see. So no, it's not that easy. Look, if you have PCET and a lot of tunneling, TJ Mayer, he has shown us, you can have isotope effect up to 50,000, 20,000, 10,000. You can say it's a PCET with a lot of tunneling. Now, in principle, H atom also tunnels, right? But that's where it gets a little iffy, how you look at it. Because H atom, if you look at how Sharon approaches it, she looks at orbitals. But then I understand the criticism. When you're looking at a proton moving, can you really apply standard chemical quantum mechanics and treat proton orbitals as an orbital? Because it has a classical nature, more so than electron. So it's a complex question. I don't want to go into this. I have ideas of how I think about it, but this is definitely not something I can tell you, look, this is black, this is white, you mix, it's gray. I cannot tell you that. Okay. Riyanka, is there any possibility to get unwanted products along with the required one? Riyanka, that's what I was trying to tell you. There are no unwanted products. if you tune your reaction, you can get selectively the unwanted product, or you can avoid getting the unwanted product, right? That's kind of what I was telling you towards the end. Sorry, very fast. Forgive me for that. That's what I was telling you. Look at this slide, right? The whole idea is this is what was wanted, oxygen reduction to water. These are unwanted, but these are highly wanted in different enzymes. And you can switch because nature uses very simple designing principles. Of course, to enhance certain reaction, it would give a different axial reaction, coordination, fine tuning the reactivity. Some proton transfer pathway with a different pK, which concerns us, who are specialists in that. But essentially, they're going to use the same basic framework, but then tune them by weak interactions to give you completely different products. Okay. All right. How stable is the catalyst after the cyclation? Pawan, the catalyst eventually dies. The 20,000 number turnover that you see, that summed over the whole reaction, the electrolysis time. But the good part is you can just wash the electrode with HCl, dilute, all the iron goes out with the porphyrin, and then you can put in fresh catalyst, which, you know, we have picomoles of catalyst on the electrode. Okay, so it's really, really less. So I don't think you would mind that much loss, given what you're getting in return. So Mohanty, welcome back. How can we think of degradation pathway? Ferril species, look, degradation pathway again. Ferril, you give it a substrate, which has a CH bond it can access in a right orientation, sigma pi, Shaikh, ed, it will do that. You don't give it a pathway, you have ligand with CH, it'll go after that. Because remember, in homogeneous solution, you're doing this. All your ferriles can do bimolecular, so they'll go after each other, right? A good solution was given by Ronnie Newman. Ronnie Newman is in Weizmann or Technion, somewhere. Brilliant guy. What Ronnie is doing, he's making high valent iron oxo on polyoxometallate. So Mojit Roy, if you're there, you're laughing. He's doing polyoxometallate, iron for oxo, because the polyoxometallate cannot be oxidized anymore. So they are more stable. And look at the paper he published in ACS Catalyst, last year. Really good. Where he's taking iron 2 on polyoxometallate, photoactivating iron 3 with oxygen light, making iron 2. Oxygen comes in, makes an iron for oxo, and it's doing transformations, tough transformations. And because of polyoxometallate, they're weak ligand, they are high spin. So that's a good way of going about it. Okay? Rahul, how do you confirm specific protonation of the proximal? Oh, Rahul, see, the advantage is you do, okay. He's asking, how do you know which oxygen is getting protonated experimentally? The answer to that is in the product. See, I told you we had an in situ product detection tool, that is the platinum ring. If you are protonating the proximal, the one bound, you're going to get H2O2. So you detect how much H2O2 you get using the platinum ring. And you detect the pH dependence of that. This is outlined in 2015 inorganic chemistry paper by Shuripto Chatterjee and Puchon. Okay? pH dependence of H2O2 gives you the pK of this, and pH dependence of the oxygen reduction rate by Shoini, which depends on the O-bond heterolysis, gives you pK of that. That's how we have approximately come to that. Okay? Now, Gaurav Pandey, can inorganic nanoparticle increase the photobleaching effect of Gaurav, I'm not a nanoparticle guy. I really don't want to second guess here. There are a lot of good nanoparticle research groups in the country. Please talk to them. I am very limited in my knowledge, and I respect knowledge. So I don't want to pretend I know what I don't know, and I hope people respect that. Saroj, how kinetics is involved? Saroj, everything in life is kinetics and thermodynamics. Okay? If you're not married, somewhere there's a woman ready for you. That's thermodynamics. How long you will get to that woman is kinetics. Some people live a lifetime. Maybe do side reactions, other woman, before realizing that's a thermodynamic minimum. Everything in life is thermodynamics and kinetics. So yes, thermodynamics is oxygen to water standard potential at pH 7, average 4 electron, 0.83. But kinetics is the excess energy you have to give to break these O bonds, okay, to do the intermediate electron transfer. So everything is thermodynamics and kinetics. All right. Diksha is back, so she's going to tell us something. Diksha, there are open 115 questions, if I'm not wrong.
Yeah, actually, I saw that. And you will be in question marathon because people will continue building their curiosity. So it can be like three. So one thing I can do, you can take probably last 2, 3 more questions, and I can send you like the all questions back to you with their email address. So
Okay,
you can
thank you, Diksha. So what I'm going to do, respecting the time, I'm going to pick the question which are most complex and directly related to what we are doing.
Absolutely.
And everything else, please feel free to write me, or maybe I'll do the other. Then I can do more questions. I will do the easy ones.
People
Okay?
can go to
Complex
Facebook
ones.
as well. Actually, your talk is live there, and they can have like those Q&A because Jyotishman took a lot of questions there as well.
Here, Facebook Live. Ooh. So I'm getting transferred live. That's interesting. Okay, now over potential of this system is really high because around 700 millivolt. Okay, Gaurav, you are asking a complex question, but my answer is principle of microscopic reversibility. Jointo CH bond hydroxylation of the not aromatic ones in my system is the distance from the high valent metal oxide center. Okay, that's what makes them separate, and a competing substrate which we are providing externally. Gaurav, active centers of OR are single molecular porphyrins. Okay, that is Shagni. Yeah, Jointo, that's good. How do you detect H22 in solution? You want to do it in electrochemistry, you can do platinum ring electrode. In solution, you can use an assay called methyl orange assay. No, forgive me, my wife is killing me somewhere. It's a xylenol orange assay, something that my wife, who works with Alzheimer and antioxidant, she uses reader papers. Devajyoti optimized it for solution in our lab. We just copy him. Shumanati, well, 3 in the morning here. Hey, sorry for disturbing your sleep. Can you produce H2 catalytically from using oxygen and H2? What do you want? Okay, what do you want next? Can I create gold after adding electrons to iron? Are you kidding me? I mean, of course, yes, this can be done, but I've not done it. I've not done it so far. It's like, you know, can you do this? Can you do that? Can I fly? Can I blow like, you know, Hulk and make Amphan go away? No, I cannot. So I'm just kidding. No, we have not done O2 and H2, H2O2. You are requested to look at, I think it's Suni Fukuzumi, his group, I know, and Alan Balch in Grenoble. They're doing it, and a group in NREL, several groups actually, forgive me, I'm bad with names, they're doing it.